Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we'll continue our conversation about exponential and logarithmic functions, specifically about the properties of logarithms. So up to this point, you should have watched the videos on exponential functions, the graphs of exponential functions, logarithmic functions, graphs of logarithmic functions, and now we're finally into all the properties that you should already know about logarithms. But this is just a review of that. So all these properties are required for you to succeed in calculus. Like none of them can be thrown out. Well, maybe change of base, but pretty much all of them are there. And what we're going to do in this video is prove a few of them. So this video is just dedicated to reminders and then to proving some. Let's go ahead and take a look at this first one. Log base b of 1 is always 0. Remember, the base here for a logarithm is always going to be positive, and it's not going to be 1. That's our restriction on the base of a logarithm. So log base b of 1 is 0. Why? The circular argument, of course. B raised to the 0th power is equal to 1. That's why log base b of 1 is 0. Let's see, and that's not, well, kind of is a language proof, so there you go. Log base b of b itself is 1. Again, because b raised to the first is actually equal to b to the first. That's why that's true. Log base b of b to the x. This is x. This is actually one of the most important ones. They're all very important, but this is very, very important. And this is true because b raised to the x power is going to equal b raised to the x power. Very, very simple to write out. Now this next one is actually not like the other ones because I can't use the circular argument here. But I might have proven this in a previous video, so I'm just going to state it out loud. B raised to the log base b of x is just x. And this is because logarithms base b and exponentials base b are inverse functions. They undo each other. A lot of students look at it this way. Oh, these kind of cancel out and just becomes the x, or these just cancel out and it becomes the x. It sort of is and sort of is not true, but visually I think that's what a lot of students think, so that's perfectly fine. Now this one is one we'll prove in a moment, but I just want to say it out loud. Log base b of a product is the sum of the log base b of m and n. So again, if you have a product as the argument of your logarithm, you could split it apart into a summation. Now I do want to mention off to the side here, there is no such property that says, oh, log base b, actually I'll write this in red. There's no such property that says log base b of m plus n is equal to log base b of m times log base b of n, nor is it, so let me just say these are not equal to, nor is it log base b of m plus log base b of n. So it's neither of those. And so we have no property that actually allows us to pull apart a logarithm that has a summation within it or a difference. You cannot do that. So there's no property that allows us to break apart the log of a sum or a difference. All right. The next property, which is the quotient property, log base b of a quotient, m divided by n, is just log base b of m minus log base b of n. So these two right here end up being incredibly important in calculus. So you have to know those and be intimately familiar with them. This next one down here is also one of the most important properties as well. Log base b of m to the p power is p times log base b of m. Good way to think about this is if the argument of your logarithm has a power on it, and if all the parts, in other words, it can't just be like, oh, I have log base b of x squared times y, let me bring out the square. No, you can't do that. That's illegal. The square has to actually be on both factors. So everything on the inside of your logarithm has to be raised to that power for you to be able to grab that power and pull it out in front of the logarithm. That is one of the most important properties for logarithms. Very, very powerful. And finally, we have, actually not final, you can see we have a few, but generally speaking, finally, we have the change of base formula. Log base b of m, well, you could change that to any base logarithm that you want. So it could be the natural logarithm, base e, or the common logarithm, base 10. Whatever you choose, it'll be log base a, where a is what you're choosing to change the base to. It'll be log base a of m divided by log base a of b. Okay, and the way I always thought about this when I was a student is that this ends up going to the numerator and this ends up going to the denominator. It's a little trick. All right, so let's go ahead and talk about the last two. The last two are just definitions. If you ever see a logarithm without a base written on it, and it's log, then you know it's base 10. It's just a silent base there. It's called the common log, and I think we talked about that in the last video in this series, but that's what it is, the common log. And then anytime that you see ln, that's an L right there, ln of x means the natural log of x, or in other words, log base e of x, but it's also more commonly known as just the natural log of x. All right, so let's go ahead and dedicate some time to proving at least one of these. The top four there, these guys, those are easily proved in your Algebra 2 course. So I'm going to go ahead and, actually all of these are proved in your Algebra 2 course, but I'm going to pick on this guy and this guy, because those two are kind of the important ones for calculus and pre-calculus. So here we go. A proof of log base b of m times n is equal to the log base b of m plus the log base b of n. Now the first thing we're going to actually do for this proof is we're just going to define what log base b of m is and what log base b of n is. So we're going to let log base b of m, because I don't know what this is actually, I'm going to let that equal x. And since I don't know what the log base b of n is, I will call that y. Just because, well, I don't know what they are, and that's okay. By the way, this implies by the definition of a logarithm, if you use the circular argument, that b raised to the x is the same thing as m, and b raised to the y is the same thing as n. Again, I don't know what x and y are. Moreover, I should say I don't know what log base b of m or log base b of n are, so I just call them x and y respectively. All right, so now let's start our proof. Let's consider log base b of the product m times n. Well, we happen to know that m, just from our designations right here, m is equal to b to the x and n is equal to b to the y. So that's what I'm going to replace those with. That's log base b of, again, m is b raised to the x power and n is b raised to the y power. And now what I'm going to do is use a law of exponents, specifically the one that says when you have like bases, you can add exponents. And we happen to know from a property of logarithms, specifically this property right here, that if you have the log base b of b to a power, that just turns into the power. So we have log base b of b to a power here. Let me highlight that power. So that should just turn into the power, x plus y. However, we know something about x and y. We know that x, we had defined it as log base b of m, and y, we had defined that as log base b of n. So I'm going to trade x and y out for those symbols. So this would be, instead of x, log base b of m, and instead of y, I have log base b of n. And if you look at the chain of equalities, that's what we would call this, a chain of equalities, we have shown that log base b of m times n is equal to log base b of m plus log base b of n. And that's exactly what we wanted to prove. So this proof is done. QED. Quod erat demonstratum. So it has been demonstrated. So that is our first proof. The other one that I wanted to do here is, and I'll just do it right down below. We're going to do a proof of the fact that the log base b of, maybe, do I need, yeah, I'm going to just call it m to the p. Prove that's equal to p times log base b of m. Now the proof style I'm going to use here is not exactly how I would normally prove this. Normally I would use something called mathematical induction, but I don't want to introduce that proof style in trigonometry. That is more of a proof style for pre-calculus. So instead, I'm going to wave my hands a little bit and just argue logically here. Now consider log base b of m to the p power. This is going to require us to recall what a power is. A power is just repeated multiplication by the base. That is, log base b of m to the p is the same thing as log base b of m times m times m, and you just continue that multiplication on and on and on until you get to m, and you do that p times. That's all a power is. It's just a repeated symbol, a symbol that tells you you're repeating that multiplication. However, we just proved something. We proved that if we have the log base b of the product of two objects, I'll call them, you could split that apart into the log base b of the first plus the log base b of the second. So that's what I'm going to do here. I'm going to take this log base b of m times a bunch of other m's, and I'm going to break it into log base b of m. Let me write that down. Log base b of m plus the log base b of all those other m's. M times dot 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 times m. But now we don't have p of these. We stole one out. We only have p minus 1 of those. And then I'm going to do the same trick here. I'm going to break that apart. That's equal to the log base b of m plus, again, log base b of m plus the log base b of all that stuff that got left over. M times dot 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 all the way down to m. This time, again, I pulled apart one of them, so I now have p minus 2 of these multiplications happening. And you get the idea. This goes for however many times p is. So you do this, if p is 10, you split this apart into 10, the summation of 10 terms. So in the end, dot, 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 and this is why I said I'm kind of hand waving a little bit when I do this. Normally you would be a little bit more rigorous with the statement, but in the end you have log base b of m plus log base b of m plus dot 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 plus log base b of m, and you did that summation p times. Now think about that. If I told you to add 3 to itself 10 times, a faster way to do that is 3 times 10. If I told you to add x to itself 10 times, you would say that's 3, that's x times 10. If I told you to add log base b of m to itself p times, it would be p times log base b of m. This is p times log base b of m. We have p of them, basically. And again, through a chain of equalities, the log base b of m to the p is equal to p times log base b of m. And we have proven that property. QED. Let me write QED down here. Quod erat demonstratum. So it has been demonstrated. So there we go. We've proven 2 of those properties. Now, I don't want to waste all of our time going through and proving a ton of properties. We should use them as well, because you're heading into pre-calculus eventually, and you want to be able to use these properties. You're very familiar with them from your Algebra 2 course, so now we're just going to go ahead and use them repeatedly in a calculus style setting. So we'll go ahead in the next video and do that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.